There are several possible reasons why an overcurrent protective device, or OCPD, did not trip in the described scenario. Firstly, consider a high impedance fault. The short circuit may have had a high impedance, meaning it allowed a very small amount of current to flow. This might not have been enough to trip the OCPD. Secondly, it could have been a transient fault. The short circuit may have been temporary and disappeared before the OCPD had time to react. Now let's explore why the short disappeared. It's possible that the short circuit occurred due to a loose or damaged connection that could have been restored when the range was pulled out. To determine if it's a range problem, consider these steps. Firstly, test the range. Disconnect the range wiring and test the range housing for continuity to ground. If there is continuity, it indicates a fault in the range. Secondly, inspect the wiring carefully. Inspect the range wiring for any damage or loose connections. Thirdly, rule out other appliances. Check the wiring and grounding of other appliances connected to the circuit to ensure they are not contributing to the issue. There are additional considerations. The 2000 ohms resistance between the sink and the ground and the nearby plug may indicate a weak ground connection. Consider inspecting and improving the grounding system. Also, consider the damaged wiring in the range. While the visible damage may not have been touching the case, it's possible that there is other internal damage that is causing the issue. Finally, consider residual voltage. Even after turning off the breaker, there may still be some residual voltage present in the circuit. This could cause a false reading when testing for shorts. Based on the information provided, it seems likely that the range is the source of the problem. To ensure safety, it's recommended to disconnect the range and have it serviced by a qualified appliance technician before putting it back into use. When dealing with electrical issues, always prioritize safety. Begin by de-energizing the circuit at the breaker before conducting any inspections or tests. Double-check that the power is off using a reliable voltage tester. Ensure your tester is functioning correctly by testing it on a known live circuit before and after testing the circuit in question. Wear appropriate personal protective equipment, including safety glasses and insulated gloves, to minimize the risk of electrical shock or arc flash. Work in a dry environment, as moisture increases the risk of electrical hazards. Avoid touching any exposed wires or components with your bare hands. Use insulated tools designed for electrical work. If you are not comfortable or experienced working with electricity, it is always best to consult a qualified electrician. They have the knowledge, skills, and equipment to safely diagnose and repair electrical problems. Remember that electrical work can be dangerous, and taking precautions is essential to protect yourself and others. When troubleshooting electrical circuits, it is helpful to have a systematic approach to identify the root cause of the problem. Here is a step-by-step guide to help you effectively troubleshoot electrical issues. Firstly, gather information. Before you start troubleshooting, gather as much information as possible about the problem. Ask questions such as: when did the problem start? What were the circumstances when the problem occurred? And has anyone tried to fix it before? Secondly, identify the symptoms. Carefully observe and document the symptoms of the electrical problem. Note any unusual noises, smells, or visual indications such as flickering lights or smoke. Thirdly, review the circuit diagram. Obtain a circuit diagram or schematic of the electrical system you are troubleshooting. This will help you understand the circuit's configuration and identify potential points of failure. Fourthly, perform a visual inspection. Conduct a thorough visual inspection of the electrical components, wiring, and connections. Look for signs of damage such as burnt wires, loose connections, or corroded terminals. Fifthly, use a multimeter. A multimeter is an essential tool for electrical troubleshooting. Use it to measure voltage, current, and resistance in the circuit. Compare your measurements with the expected values to identify any discrepancies. Sixthly, isolate the problem. Once you have identified potential problem areas, try to isolate the issue by disconnecting or removing components one at a time. This will help you narrow down the source of the problem. Seventhly, test for continuity. Use a multimeter to test for continuity in the circuit. This will help you identify any broken or open circuits. Eighthly, check for shorts. Test for shorts by measuring the resistance between different points in the circuit. A short circuit will typically have a very low resistance value. Ninthly, replace faulty components. Once you have identified a faulty component, replace it with a new one that meets the specifications of the original component. Tenthly, test the circuit. After making any repairs or replacements, test the circuit to ensure that the problem has been resolved. Use a multimeter to verify that the voltage, current, and resistance values are within the expected range. Remember to always energize the circuit before making any repairs or replacements. If you are not comfortable performing electrical work, it is best to consult a qualified electrician. Grounding is a critical safety feature in electrical systems, providing a low impedance path for fault current to return to the source. This path allows the overcurrent protection device, such as a circuit breaker or fuse, to quickly trip and to energize the circuit, preventing electrical shock and minimizing the risk of fire. Ears-wide grounding is essential. Firstly, it provides a low impedance path. Grounding creates a low resistance path for fault current to flow back to the source. This low impedance path ensures that the fault current is high enough to trip the overcurrent protection device. Secondly, it limits voltage. Grounding helps to limit the voltage on electrical equipment and appliances. This prevents dangerous voltage buildup that could lead to electrical shock. Thirdly, it protects against lightning strikes. Grounding provides a path for lightning strikes to safely dissipate into the earth, protecting buildings and equipment from damage. Fourthly, it reduces electrical noise. Grounding can help to reduce electrical noise and interference in sensitive electronic equipment. Fifthly, it enhances safety. Grounding significantly enhances the safety of electrical systems by reducing the risk of electrical shock, fire, and equipment damage. There are different types of grounding systems, including equipment grounding and system grounding. Equipment grounding connects the metal parts of electrical equipment to ground, while system grounding connects the neutral point of the electrical system to ground. The National Electrical Code, or NEC, provides detailed requirements for grounding electrical systems. These requirements are designed to ensure that grounding systems are properly installed and maintained to provide maximum safety. It is essential to follow the NEC requirements when installing or modifying electrical systems. If you have any questions or concerns about grounding, consult a qualified electrician. The OCPD, or overcurrent protective device, is a critical safety component in electrical systems, designed to protect against overloads and short circuits. It works by interrupting the flow of current when it exceeds a predetermined level, preventing damage to equipment and reducing the risk of fire. There are two main types of OCPDs. Firstly, circuit breakers. Circuit breakers are electromechanical devices that automatically trip and interrupt the circuit when an overcurrent condition occurs. They can be reset and reused after the fault has been cleared. Secondly, fuses. Fuses are single-use devices that contain a fusible link that melts and breaks the circuit when an overcurrent condition occurs. Fuses must be replaced after they have blown. OCPDs are rated in amps, which indicates the amount of current they can safely carry before tripping or blowing. The amp rating of an OCPD should be selected based on the load it is intended to protect. The National Electrical Code, or NEC, provides detailed requirements for the selection and installation of OCPDs. These requirements are designed to ensure that OCPDs are properly sized and installed to provide adequate protection against overcurrents. It is essential to follow the NEC requirements when selecting and installing OCPDs. If you have any questions or concerns about OCPDs, consult a qualified electrician. When troubleshooting electrical circuits, it's important to understand the difference between an overload and a short circuit. These are two distinct types of overcurrent conditions that require different approaches to diagnose and resolve. Firstly, an overload is a condition in which the current flowing through a circuit exceeds its rated capacity. This can be caused by connecting too many devices to the circuit, or by a malfunction in one of the devices. An overload typically results in a gradual increase in current which can cause the wires to overheat and potentially start a fire. Secondly, a short circuit is an unintended connection between 2 points in a circuit that have different voltage potentials. This can be caused by damaged insulation, loose connections, or accidental contact between conductors. A short circuit typically results in a sudden and dramatic increase in current, which can cause the overcurrent protection device, OCPD, to trip or blow. Here's how to differentiate between an overload and a short circuit. In an overload, the current gradually increases over time. The wires may feel warm or hot to the touch, and the OCPD may trip after a delay. In a short circuit, the current increases instantaneously. There may be a loud pop or flash at the point of the short, and the OCPD typically trips immediately. To troubleshoot an overload, firstly, reduce the load in the circuit by disconnecting some of the devices. Inspect the wiring for any signs of damage or overheating, and ensure that the OCPD is properly sized for the load. To troubleshoot a short circuit, firstly, de-energize the circuit and visually inspect the wiring for any signs of damage or loose connections. Use a multimeter to test for continuity between different points in the circuit and repair or replace any damaged wiring or components. Remember to always follow proper safety precautions when working with electricity. If you are not comfortable or experienced working with electrical circuits, it is best to consult a qualified electrician. When dealing with intermittent electrical problems, it can be challenging to pinpoint the root cause. These types of issues occur sporadically, making it difficult to capture the problem in real time and gather reliable data. However, by employing a systematic approach and utilizing various troubleshooting techniques, you can effectively diagnose and resolve intermittent electrical problems. Firstly, gather information. Collect as much information as possible about the problem, including when it occurs, under what conditions, and any patterns or trends you observe. This information can provide valuable clues about the potential cause of the intermittent issue. Secondly, monitor the circuit. Use a multimeter or other monitoring devices to track the voltage, current, and resistance in the circuit over time. This can help you identify any fluctuations or anomalies that may be contributing to the problem. Thirdly, check connections. Inspect all electrical connections in the circuit, including wires, terminals, and connectors. Look for signs of looseness, corrosion, or damage. Tighten any loose connections and clean any corroded terminals. Fourthly, test components. Systematically test each component in the circuit to rule out any faulty parts. Use a multimeter or other testing devices to verify that each component is functioning properly. Fifthly, consider environmental factors. Environmental factors such as temperature, humidity, and vibration can sometimes cause intermittent electrical problems. Consider whether any of these factors may be contributing to the issue. Sixthly, use a data logger. A data logger is a device that can automatically record electrical parameters over time. This can be helpful for capturing intermittent events that occur when you are not present. Seventhly, divide and conquer. If the circuit is complex, try dividing it into smaller sections and testing each section separately. This can help you narrow down the location of the problem. Eighthly, be patient. Intermittent electrical problems can be frustrating to troubleshoot. Be patient and persistent, and don't give up until you have found the root cause of the problem. Remember to always follow proper safety precautions when working with electricity. If you are not comfortable or experienced working with electrical circuits, it is best to consult a qualified electrician. Electrical resistance is a fundamental property of materials that opposes the flow of electric current. It is measured in ohms and is denoted by the symbol R. The higher the resistance of a material, the more difficult it is for current to flow through it. Several factors can affect the electrical resistance of a material. Firstly, material type. Different materials have different inherent resistances. Conductors such as copper and aluminum have low resistance, while insulators such as rubber and plastic have high resistance. Secondly, temperature. The resistance of most materials increases with temperature. This is because the increased thermal energy causes the atoms in the material to vibrate more, which impedes the flow of electrons. Thirdly, length. The resistance of a wire is directly proportional to its length. A longer wire will have a higher resistance than a shorter wire of the same material and cross-sectional area. Fourthly, cross-sectional area. The resistance of a wire is inversely proportional to its cross-sectional area. A thicker wire will have a lower resistance than a thinner wire of the same material and length. Fifthly, impurities. The presence of impurities in a material can increase its resistance. Impurities disrupt the flow of electrons and make it more difficult for current to flow. Electrical resistance is an important factor to consider when designing and troubleshooting electrical circuits. It affects the amount of current that will flow through a circuit, the voltage drop across components, and the amount of power that will be dissipated as heat. Ohm's law is a fundamental relationship in electrical circuits that relates voltage, current, and resistance. It states that the voltage across a conductor is directly proportional to the current flowing through it and the resistance of the conductor. Mathematically, Ohm's law is expressed as voltage equals current times resistance, or volts equals amps times ohms. Ohm's law can be used to calculate any one of the three variables if the other two are known. For example, if you know the voltage across a resistor and the current flowing through it, you can calculate the resistance using the formula resistance equals voltage divided by current, or ohms equals volts divided by amps. Ohm's law is a powerful tool for analyzing and troubleshooting electrical circuits. It can be used to determine the expected voltage, current, and resistance values in a circuit, and to identify any discrepancies that may indicate a problem. For example, if you measure a voltage drop across a resistor that is significantly different from the value predicted by Ohm's law, it may indicate that the resistor is faulty or that there is a problem elsewhere in the circuit. It's important to note that Ohm's law applies only to linear circuits, meaning circuits in which the resistance is constant regardless of the voltage or current. Some electrical components, such as diodes and transistors, are nonlinear and do not obey Ohm's law. When working with electrical circuits, it is essential to follow proper safety precautions. Always de-energize the circuit before making any measurements or repairs. Use insulated tools and wear appropriate personal protective equipment such as safety glasses and insulated gloves. If you are not comfortable or experienced working with electricity, it is best to consult a qualified electrician.